Well, so today I want to discuss first of all the orthogonality relations. And many consequences of these relations. So let me remind the basic notation. So G is a finite group, and I will write often T and H is a representation of finite dimension. T is the symbol of representation, and H is the representation space. And I also use the alternate notation that H is H of T. And next, G hat is the set of equivalency classes of irreducible representations. I will simply write irreducible representations. Well, and I recall also an important result that any representation T can be made unitary.
Ого.
I'm sorry, please switch off the microphone. So T is unitary, which, I'm sorry, excuse me, please. Please switch off the microphone.
Антон, отключи микрофон, пожалуйста.
T is unitary, which means that there exists a scalar product in H such that our operators are unitary. So each operator T of G is unitary with respect to this scalar product. And next, let me start with the following lemma. So assume that we have two irreducible representations, this one and T prime, this one. So these are irreducible. So write it as follows. And we are interested in sequilinear forms. Sequilinear forms, say phi, which is a map H cross H prime to our base field of complex numbers. And sequilinear means that it is linear with respect to this variable and antilinear with respect to this one, and assume that it is invariant. Assume phi is invariant. Phi is invariant, which means the following, that we apply, we have two vectors, psi prime, and then the relation which is required is as follows. Prime G T prime is the same as this one for any element of G. Okay. So in this case, we say that this formal map is invariant. Now we have a following claim. So first, assume that T and T prime are non-equivalent. But there is no such form. So this implies that phi is equal to 0. And next, assume that they are equivalent. So simply we assume that T is equal to T prime. And so H is the same with H prime. And then it follows that phi is proportional to the scalar product. So up to some constant, we have this relation, which is satisfied for the scalar product, and there are no other possible sequilinear invariant forms. How to prove this? But this is quite simple, a pure linear algebra. So we prove. Linear algebra, which means that in general, any phi can be written as follows. There exists some operator A, which can be applied, and where A is an operator, linear operator from one space to another space. And any sequilinear form can be represented in such a way. And then invariance just means that A is a intertwining operators. Oh. But we know by Schur lemma implies immediately that it's impossible if the representations are non-equivalent, and if they are equivalent for claim 2, we have that A is necessarily an intertwining operator for our representation, so it's a scalar. And this means that we have this relation. So this implies. Okay. So please ask if something is not clear. Okay.
А что такое sequilinear по-русски?
Полуторалинейный.
А может, тогда, what does it mean?
Полуторалинейный? What does this mean? Okay, this means, I said this. Okay, I will repeat. This is a map which is linear with respect to one variable and antilinear with respect to another variable. Just as a scalar product, which is linear with respect to one variable and antilinear with respect to another. Okay?
Thank you.
Okay, well. So please ask questions. No problem. Well, now I need a definition. So assume T, H, a representation. What is a matrix element? Matrix element of it is a function. So it's a function on the group. So it's an element of the space of functions on our group of the form as follows. It depends on two vectors, psi and eta. I'm sorry, I would like to say that I will assume that our representations are unitary. So we have a fixed invariant scalar product. So the function in question is the following. So this is my scalar product, and this is a function on G. So this is a matrix element which corresponds to a couple of vectors, psi and eta. And what next? Next, a little definition. I want to fix a scalar product. In our space of functions as follows. Given two functions, the scalar product is defined by the usual formula. The sum of this expression, but I want to divide it by the order of the group. Why? Somebody already asked me why to do this, and the reason is as follows. Actually, what I want to say can be extended to the case of compact group. And for compact group, it's reasonable to work with the normalized Haar measure. So this scalar product is just the scalar product in the L2 space of our group. It's a finite set, but nevertheless, with respect to some measure, what is this measure? This is the so-called uniform distribution, which assigns to any point, any element small g, the weight which is equal to 1 over the order of the group. And so it's a probability measure. And because of this fact, it's reasonable and natural to introduce this factor. But formally, this is just an agreement. Okay? And now I want to state the result, which is a fundamental fact. This is orthogonality relations for matrix elements. It's formulated as follows. So assume again that we have two irreducible representations, T1, and T prime. So this notation just means that they are irreducible, I recall, and pick some arbitrary vectors in one space and another couple vectors in another space. And the claim, again, there are two claims. One claim is if T and T prime are non-equivalent, then the claim that the corresponding matrix elements are orthogonal with respect to our scalar product. Orthogonal. And the next case, so assume that T is equivalent, and then it is convenient just to assume that T is just equal to T prime. And then we have the following formula for the scalar product of two matrix elements, which reads as follows. So we take 1, number, take the scalar product, and the result is as follows. A constant factor, D is the dimension of our presentation, which is the same the dimension of a space, so this is factor. And next we have the following product. So
I'm very sorry, but could you go back to the lemma? I kind of got left behind and can't catch up.
To go behind the lemma. Okay,
Ну,
and what we are? Say in Russian, maybe it will be easy.
да-да-да, извините, я просто отстала и теперь вообще не успеваю. Можно просто сейчас условия леммы и, значит, что
Хорошо, давайте
происходит,
я
когда...
скажу по-русски, чтобы было быстрее. Значит, утверждение такое, что если у вас есть два неприводимых представления, если мы интересуемся полуторалинейными инвариантными формами, то таких форм вообще нет, если эти два представления не эквивалентны. А если речь идет об одном и том же представлении, то всякая инвариантная полуторалинейная форма – это просто скалярное произведение, умноженное на постоянный множитель, ну, который, да, просто на постоянный множитель.
Ага, спасибо. И доказательства через
Ну,
слетающий
Лемма
оператор. Да,
Шура,
все, спасибо.
Лемма Шура. Доказательство через Лемма Шура такая, в том,
Угу.
что я сейчас рассказываю, такая отмычка от всего. Все сводится к Лемме Шура. Ну, до некоторого времени все будет так выводиться из Лемма Шура. Так,
А что
вот,
было простите, что было за утверждение сразу после леммы перед теоремой? Там же что-то другое было, да?
нет, ничего, по-моему, не было. Я объяснял, что такое матричный элемент.
Матричный элемент. Сейчас.
Вот я написал. Вот это матричный элемент. Функция на группе, которая задается вот этой вот формулой. Так,
Сейчас.
ну вот она формула, я ее показываю, смотрите.
Да-да-да-да-да, все, спасибо, поняла, спасибо.
Нормально?
Да, спасибо.
То движемся дальше. So let me give a proof. The proof relies on the lemma. So introduce some object, again denoted by phi, psi1, psi2, eta1, eta2, which is just the scalar product in question. So this is scalar product, and the formula is written here. I'm sorry, maybe it's better to reproduce it again to make the proof easier. So I'm sorry for repeating, but maybe it's better to do that. And next, I went side 2, it 2 bar. Okay, so this is just the definition. Again, some microphone switch off.
Oh, sorry, that's me.
Thank you. Okay, so this is my notation, and look on that. So my claim is as follows. So if you fix these variables, we get a sequilinear form in psi1 and psi2, and it is invariant. It's easy to verify. And likewise, this is also a form, if the xi's are fixed, this is a form which is sequilinear, namely it is linear in this variable and antilinear in this variable. And by the lemma, this implies that this is equal to some constant times the scalar product question. And bar, because, so it's easy, I think it's easy after I wrote this relation, this definition, okay, and looking at this expression, it's easy to see, to memorize in what variable is it linear and in what variable is it antilinear. Okay? And now we see immediately if T is non-equivalent to T prime. This means that, first of all, this makes no sense. This makes no sense. Even this representations is absurd. So I would like to say that if representations are non-equivalent, then phi is 0. So this makes sense. I'm sorry, for the case T is T prime. So first, I had to say first that we have this conclusion. But now, assuming that T is equal to T prime, we have this implication. And now it remains to compute the constant. Compute the constant, and how to do that? To do that, let's take psi1 equal to psi2 equal to some vector psi, and pick a basis, orthonormal basis in H, and take E1 equal E2 equal to one of these basis vectors, and then sum over I. And what we get? And then we get the following equality. We get the following equality. Sum over and the double sum, because I want to make summation over I, and we have this expression next. This one, bar, and this is equal to D times our constant, and this is equal to the squared norm of psi. Why? Because looking at this sum, okay, we just get this variable, and because yes, I think it's correct. Okay, and so, and this is on the right-hand side, and this is equal, to this expression. Okay. So this comes from the right-hand side, and comparing this to this, and because our operator T of G is unitary, we conclude that C is equal to 1 over D. So this is just we want. we want here. So this is the proof. If something is not clear, so please just take a little time and repeat the computation, and you will see that it's correct. And from this theorem, there are many consequences, and let me try to explain. So some little formalism. So let's, for a moment, see H be a unitary representation, not necessarily irreducible. And let's consider the space of all operators and endomorphisms, all linear operators on our space. So this is a linear space. If our space H has some dimension, say n, then this is also a linear space of dimension n squared. Okay, so this is obvious. So I want to introduce a scalar product in this space. So for two operator and B, I define the scalar product as follows. Take the product A, B star. Star means taking the adjoint operators. And because our representation is unitary, this is a finite dimensional Hilbert space or Euclidean space as we want. So there is the notion of adjoint operator. Take the product and take the trace. Take the trace. Is it clear what happens here? So please ask questions. Okay. And so we have another space, and I want to introduce a representation, and actually a unitary representation. A unitary representation on this space of what? Of the double. I mean the product of two copies of our group. So what is the action of this group? So let's denote it by the tilde. So now we have two elements, one from each copies, and it operates on an operator A, maps it to this operator.
А оператор A лежит в эндоморфизмах H.
Да, это просто оператор в пространстве H. Нормально, да? Пожалуйста, спрашивайте что-то.
А можно еще раз, что такое B со звездочкой?
Ну, это линейная алгебра. Это сопряженный оператор.
Сопряженные, спасибо. Это просто несколько разных вещей обозначает иногда. Извините.
Да, нет, вы не извиняйтесь, пожалуйста, спрашивайте. Мое дело отвечать на вопросы. Не стесняйтесь. Okay, so we have a representation. It's easy to see, first, that it is indeed a representation. And next, it is unitary. So it's easy to see because our initial representation is unitary. Okay? And what is this representation? So we claim that this representation, T tilde, is, say, equivalent, is the same as what? As the exterior tensor product. So I want to distinguish between the interior tensor product and exterior. Let me explain. And TBar. What means TBar? What is TBar? TBar is the dual representation to T. What means dual? If you have a representation on a space, in finite dimensional space, then our group acts on this space, and then it acts on the dual space, the space of linear functions, and we get another representation which is said to be the dual to the initial representation. And the dual to dual is the initial representation. Okay? But in our situation, we have unitary representation. And because we have a scalar product, which is equilinear, we have a possibility to realize the dual representation on the same space, to identify the dual representation with the initial representation, but with the agreement that we change the complex structure, which means that we introduce another, the conjugate complex structure. If you want to multiply a vector by a scalar, lambda, say, which means that in our new space, we have to multiply it by lambda bar. So this is, again, linear algebra. In the presence of a scalar product, the dual space can be identified with the initial space with the agreement that we change the complex structure. Okay? So if something is unclear, so please recall that this is linear algebra. So we should understand this. Okay? So why I want to make this symbol? Because I want to write this one for the usual, for tensor product of the same group. So the interior tensor product of two representation is the representation of the same group. And the exterior means that we take, in general, it may happen that we have one representation of one group and another representation of another group. Then we can take the tensor product, exterior tensor product of the direct product of two groups, which in principle can be different. And if you want to consider tensor product of the same group, the interior one, then we have to restrict this to our group G with respect to the diagonal embedding. Okay, restricting the exterior tensor product to the diagonal subgroup, we get the interior tensor product. So a little formalism. Okay. So the claim. So I want to return to the claim. This is a claim. This is a claim. So why? Why is it equivalent? But this is because, this is the answer is because, again, linear algebra, again, this is a claim from pure linear algebra, not representation theory, but pure linear algebra. Because and H is canonically isomorphic to this one. In general, the space of linear operators on a finite dimensional vector space can be identified in a canonical way to the tensor product of our space times the dual space. But because we have a scalar product, we can identify the dual space with the initial space by changing the complex structure. And so from this claim, from this identification, we get this claim. So please fix this claim. I will need it. And well, what next? I want to introduce one definition, namely, if you have some psi from our space H and some vector eta from the dual space, again identified actually with the initial space. Let me assign to it the operator how to write it. Maybe I will write it as follows. This is an operator. And the definition is as follows. I want to define what is the action of this operator on a vector. And the definition is as follows. If I want to apply to some vector x, the result is as follows. We take the scalar product with eta and multiply by xi. So this is a scalar. This is a scalar, and this is a vector. If you know the notation of Dirac in Dirac notation, Dirac's notation, Dirac's notation from quantum mechanics, this can be written as follows. Let me write it as follows. So this is, but I don't want to insist on this. If you know a little bit the notation from quantum mechanics. So this is the bra and ket vectors. This is I'm using notation of Dirac. Okay. So let me emphasize that this object is linear in xi and anti-linear in eta. This is seen from the right-hand side, because this is linear and this is anti-linear. Okay. So this is a linear operator of rank 1. Rank 1 operator. On yeah. So a little remark. Remark is if you take the scalar product and what is the scalar product? I mean, the scalar product in the space N of endomorphisms. And it is equal by the very definition. By the very definition of this rank 1 operator. And what next? The next step is that I want to slightly generalize the notion of matrix elements. So let's A be an arbitrary operator. And I assign to it a function on our group, which is defined as follows. The value at G is equal to the trace of the product of these two operators.
А область значения в поле лежит вот этих функций?
Все комплексно значено, все у нас под полем комплексных чисел. Ну, там какие-то вещи на самом-то деле можно было бы этого избежать, но давайте не будем заниматься сейчас обобщениями. Все базовое поле, основное поле комплексные числа. So remark, which is easy to verify, that if A is this rank 1 operator, then it's the matrix elements in the initial, from the initial definition. So this is just an extension of his notion. So it's easy to verify. Indeed, easy. So as a corollary, we get the first corollary from our result. We get So assume that T and T prime are irreducible as before, and A is one operator. I mean, H is the corresponding space, and A prime is from another space. And again, these generalized matrix elements are orthogonal. Why? But because these generalized matrix elements are nothing else than linear combinations of initial matrix elements, rank one can say matrix elements. So this is a direct corollary. This is the first claim. And the second claim is as follows. So assume T and T prime are the same. Equivalent, but then we can assume that they are just the same. And then the scalar product, and maybe I'm sorry, let me change the notation. It will be that I will write B, A and B. Okay. And then the scalar product is equal to 1 over D, and D is the dimension, and the scalar product of in this space. I recall that this is the scalar product in the space of operators. So again, it's easy. It's a direct corollary. And what next? What next? The next we can construct a map, a linear map. We construct a linear map. A linear map. I don't want to introduce a special notation, just to write it. So we take a direct sum of over all representations. As it often happens, I will identify equivalence classes and simply representations, irreducible representations. So take all irreducible representations, take the direct sum of these spaces. Okay. And we map it into the space of functions on G, just as follows. So if A is in one component in some H of T, then A is mapped. We take the dimension, square root, and the corresponding generalized matrix elements. Okay? So with just a little correction. So this is a little correction, which comes from this. And so we claim, what I claim. First,
А A принадлежит эндоморфизмам или H?
нет. A у меня большими буквами это оператор. Это оператор, то есть элемент пространства эндоморфизма.
У вас
Понятно?
просто на нижней сейчас строчке написано, что оно из H.
Ба-ба-ба-ба-ба-ба. В самом деле. Спасибо.
Спасибо.
Тогда вы совершенно правы. Это мой ляп. Спасибо. Поправляйте, пожалуйста, не стесняйтесь всякий раз, если я делаю такого рода глупости, да. So what I want to claim, so this is linear, this is obvious, this is injective. Why injective? And this is a corollary of the orthogonality relation. And moreover, it is not only injective, it is isometric. And hence it is injective. isometric, because just because of this property and this one. So different components are mapped into mutually orthogonal subspaces, and inside each component we have isometry because this constant factor is compensated by this one. This is the same D, which is here. Okay? So it's isometric, an isometric embedding. And the next claim, it is G cross G invariant, which means that it is meaning it is an intertwining operator. In what sense? Okay, so look again. We have a representation of G cross G on each this space, on each operator space. As a consequence, we have a representation on the direct sum. This is the direct sum of representations. And next, we have a representation of G cross G on this space, the biregular representation. So I have to be a little bit more precise. So what I mean by biregular representation, biregular representation of G cross G on the space of function, because there is a little ambiguity and I want to be precise. So this is my notation for a biregular representation. So given two elements, that is an element of this group, and we want to apply it to some function f and evaluate at h. This is by definition the following. We take f, h, g1 on the left, and g2 inverse, oh, sorry. This is H, G, G1, G2, G cross G. So a little ambiguity is that I could replace G1, I could switch G1 and G2, okay? But if I want to define the action of G cross G on operators, my action is as follows. Corresponding action is right. This is the action on the space of operators, applying an element of a double group to an operator A produces this expression. And to make it compatible with this map, we have to define the biregular representation by this formula. And this is easy to verify, that we have the intertwining property under this agreement. So this is an intertwining operator. So it's easy. It's easy. It's direct verification, just from the very definition. So please do it yourself. But a little bit non-trivial fact is as follows. Lemma. So I need some notation from this. I don't want to introduce something, but just denote it by star. So a linear map which which is defined by this form, okay? From this formal direct sum to the space of functions. And the claim is that psi is onto, subjective. Why? So it requires a proof. So let me give a proof. It's not absolutely trivial, it's easy.
А он-то это имеется в виду селективное?
Selective, subjective. Subjective. Okay. So the proof. The image of our map is, because it's in, we have an intertwining map, is an invariant subspace. Invariant with respect to the double action from the left shifts by the left shifts and by the right shifts. Invariant with respect to the biregular representation. So we need to prove that it is actually an isomorphism. So we have to prove that this subspace is actually the whole space. So take its orthogonal complement. Orthogonal complement. And our representations are unitary. And the orthogonal complement is also invariant because the representation is unitary. And we want to prove that it is actually zero. Why it is zero? Because it is some invariant subspace, and we have a representation of our double group. It's enough at this point to take even one-sided representation. So take say left, or right, regular representation on this orthogonal complement. We have something, some representation. We can decompose it in irreducible components. And there are some, if you have some irreducible component, we have some matrix coefficients. And these matrix coefficients, one can see, this is a little step to see, one can see that to verify this, the matrix elements of these representations on this space are inside this space. This is a fine point. It can be verified. And it follows they are orthogonal. They are orthogonal to all for all matrix elements for all T, but this is absolute. So the conclusion is that actually it's impossible. And actually, so the fine point is this one. So this one, that the matrix elements of the representations in the space of functions, in this orthogonal complement, are itself, themselves are contained in this space. So please try to verify, and if not, I will explain it later, next time, because I want to move further. So this is the conclusion. So this is the proof. So we get an isomorphism. So we have a theorem. Our map is an isometric isomorphism commuting with the action of E. So this means that a biregular representation is equivalent to the direct sum of exterior tensor products, and each component here is the exterior tensor product of some irreducible representation times the dual representation. And in particular, as a corollary, if you take one-sided left or right regular representation and they are equivalent to each other, because if you take the map G to G, which maps G small to its inverse, this gives us an identification of left representation, of left regular to right regular representation, so they are equivalent. So the one-sided regular representation is equivalent to the direct sum, again, over all irreducible representations. And each irreducible representation is contained with multiplicity equal to its dimension. So this is another fundamental fact. So we know the structure of a regular representation and of a biregular representation. For certain groups, TBar, the dual representation, is equivalent to T itself. For instance, we will see that for the finite symmetry group, they are equivalent. So in that case, one could drop bar and simply write T tensor to Ft. But for some other groups, it's wrong. So we have to distinguish between T and the T bar. So this depends on the group.
Excuse me, where did the dimension of T come from in the last line?
So did I understand correctly that you ask why this implies this?
Yes.
So this is because if we restrict, say you restrict to the first factor, what happens? So this is a representation of G cross G, okay? And so restricting just means that we take here the unity. So this disappears and produces this factor, which is equal, the dimension of this is equal to this one. If we restrict to the second factor, we get the same until we get the sum over T bar, but this is the same, exactly because there is no difference. The summation over T or the summation over T bar is just the same. It's clear or not clear?
Thank you, I understand now.
Okay. Okay. What is next? The next claim is as follows. The order of a group is equal to the sum over the irreducibles and squared dimensions. Such an identity. So this is trivial, just count the dimensions. The dimension of the representation space on the left is equal to the order of the group, because these are functions on the finite set on G, and so it's trivial. And here, this is the dimension on the right. This is the dimension on the right. This may seem to be some trivial thing, but it's very important. I would like to emphasize, because this is a very important fact. One of the reasons, only one of the reasons is false. So some informal corollary. So this space is equipped with a natural probability measure. Namely, the weight of some T, an element of this finite set, is, by definition, its squared dimension divided by the order of the group. So this is a positive quantity, and the sum of all these quantities equals 1. So this gives us some probability measure. Of course, on any finite set, we can introduce the uniform distribution. For these probability measures, all points have the same weights. And this is something different. We have some different measure. It's often called the Plancherel measure. I don't like this term, in fact, because it's a little bit incorrect from some point of view, but nevertheless, it is a conventional term. So let me just mention it. So for any finite group, and we take the dual space, and the dual space is the set of irreducible representations, it comes with a certain probability measure. For instance, I will explain later what happens for a symmetric group. On the dual space to the symmetric group, that means the set of labels of irreducible representations, which are the Young diagrams of a given size. This set is equipped with a good measure, very interesting measure, the Plancherel measure, and one of the well-studied problem in combinatorial probability or probabilistic combinatorics, I don't know how to say better, is to study the behavior of these probability measures as the group becomes, the symmetric group goes to infinity, in the sense that its size, the number n, of points which are permuted goes to infinity. So this is just a remark for future to explain why this is interesting. And I would like to go further. So the next topic, which is necessary to discuss, is the characters of representations. Characters of representation. So given the definition, so if T is a representation, not necessarily irreducible, then its character is a function on the group. And the definition is as follows. Its value at G is equal to the trace of the corresponding operator. Let me introduce some notation. I don't know how to. Okay, so I would like to write as follows. These are, in Russian, it's called центральные функции. In English, class functions. So these are functions which are constant on conjugacy classes. Class functions, which is a subspace in the space of all functions. So we have a theorem. The characters.
Sorry, again, what's the definition of the class functions?
The definition. Okay, the definition. F is class if in G, which means that the function is constant on any conjugacy class. Okay? Yeah. So the characters of irreducible representations form an orthonormal basis in this space, the space of center of class functions. So the proof. Why orthonormal? This is easy to see. This is because by the very definition of a character, so say T is irreducible, and take a basis, orthonormal basis, in the space of our representation, and D is the dimension. And then by the very definition, is the same as the sum of diagonal matrix coefficients. Okay? And again, apply the orthogonality relations. And applying them, we see first that the characters of distinct irreducible representations are orthogonal. As a consequence, they are linear independent. And next, they are orthonormal because one can verify again from the orthogonality relations that the squared norm is equal to 1. So they are orthonormal. And finally, we need to prove that they form a basis, so that the linear space, the linear span of the characters is the whole space of central functions. And how to see this? So assume, so prove that the linear span of is the whole space of central functions. How to do this? So take F. So take F, which is central. And using the previous result, we can write it as the sum over the irreducible representation of what? Of certain generalized matrix coefficients. A sub t is some operator in the space. Okay? So we have this by our previous result. But so this this claim holds for any function, arbitrary function. But now we want to use this property. And this property means that our function is invariant. Invariant under what? Under interior automorphisms of our space. I mean, here, invariance. So F is invariant under what? The change of variables. G is mapped to H, G, H inverse. Okay. But now the correspondence, we know that the correspondence between F and this representation on the right hand is equivariant with respect to the action of G cross G, because this is actually, I wrote it in the other direction in this one, okay? This is an intertwining operator. So moreover, it is equivalent with respect to this action, the conjugation action. Okay? But the left-hand side is invariant, the right-hand side is also invariant. And what this means? This means that it is invariant with respect to conjugation on A. So on the right-hand side, we have invariance under AT replaced by but what this means? This means that our operator AT is an self-intertwining operator. It intertwines our representation with itself, but it is irreducible. So by the Schur lemma, by Schur lemma, AT is a scalar operator. But what means if we take the generalized matrix element corresponding to a scalar operator, this is a scalar multiple of the character. Because if you take for this operator the identity operator, this object is just the trace. Okay, so we conclude that our invariant our class function is a linear combination of the characters. Okay, so is it clear? So now the question. My time is over. What you want? I can to spend some. Maybe may I take 5 minutes? If you want to, you can.
Yes, sir.
Okay. So I'm sorry. So I would like, because you need it for the seminar. So the seminar, I would like to state the following result. This is called the second orthogonality. Orthogonality relation. Or sometimes it's called the orthogonality relation of a second kind. It is as follows. It is as follows. So assume that G and H are two elements of our group, and we have a following identity. In the orthogonality relation, we have summation of the group. And here we have a summation over the dual space, the space of the irreducible representations. So we take one character, this character but evaluated at H, again bar, and the claim is it's equal to what? This is 0 if G is not equivalent to H, meaning that they are in different conjugacy classes. Okay? And it's equal to the order of the group divided by the order of the class if G and H are in the same conjugacy class. Okay. So how to prove this? The proof is easy. So the proof is as follows. So we know that the irreducible characters form a basis, an orthonormal basis in the space of class functions. But you have another basis. Another basis. Let me denote it as follows. So C ranges over the set of conjugacy classes. And this is just the characteristic function. Characteristic function of C, which is a function which equals 1 on this class and 0 otherwise. So this is a basis. It's obvious. What is also obvious? This basis is orthogonal. It's not orthonormal, but it's easy to see what is the squared norm of this class, of this characteristic function. It is equal to this quantity. Just take into account the very definition of the scalar product in the space of functions, which includes the factor 1 over the order of G, which explains the appearance of this quantity. And this quantity appears because this function, the support of these functions, contains exactly this number of points. So it's easy. So we have two orthonormal bases, okay? And so we have a transition matrix between these two orthonormal bases. And this transition matrix is orthogonal. And we just use the fact that the rows and the columns of an orthogonal matrix are orthonormal, okay? Orthonormal vectors. So applying this, we get this claim, just counting the how to say it, if you have an orthogonal matrix and take the sum of the squared norm of the rows or the columns, and all these quantities should be equal to 1. And this constant just comes from this one. We have just to renormalize this function to get an orthonormal basis. So I'm sorry, let me stop at this moment. I want to switch off the recording.